this is a table that breaks down Merrim's performance improvements in several key categories that we often showcase. We'll start at the top where it says SO3. So the system was designed to meet 5 ppm or less SO3 at the air heater inlet, from 70 ppm of SO3 down to 5 at the air heater inlet.
Yeah.
And you get additional SO3 removal through the back end. So your SO3 at the stack is further reduced all the way down to half a ppm. Effectiveness of the system here was over 99%. And that, as we discussed earlier, has allowed you guys to reduce your gas outlet temperature from 350 degrees down to 250 degrees,
Correct.
which is a significant reduction in your coal consumption,
Yep.
or to say it another way, an improvement in your heat rate, which related to a coal consumption reduction of about 2%.
Correct.
2% reduction in coal burned is also a 2% reduction in CO2 emitted out of the stack. I know that's not currently a regulated pollutant, but it's important to note moving forward. We talked a little bit about NOx removal. So since the SO3 is removed upstream of the SCR, you have the ability to increase your ammonia slip to drive down your NOx removal. That can result in a stack NOx emissions reduction from 80 milligrams down to 10 milligrams. So that's an 88% of additional NOx removal that you guys can leverage. Minimum operating temperature of an SCR is important. Minimum operating temperature is a function of ABS formation, which is a function of SO3 concentration, ammonia concentration, and temperature. So with removing the SO3, it reduces the formation temperature of ABS, allowing you to reduce your minimum operating temperature from 620 Fahrenheit down to 535 Fahrenheit. So it gives you the opportunity there to run it down further in terms of minimum operating temperature, or in this table we call it SCR, flexible operation. One of the other co-benefits by reducing the temperature of the gas going through the ESP, it actually slows the gas down going through the ESP, which improves the performance of the ESP as it's a function of the velocity of the gas moving through. And so we've characterized here your particulate matter reduction was 90% from its previous point due to that benefit. Here at Merrim, you guys also have a HBS system. So you have a small dosing of sodium bromide into the SBS system as it goes up to the injection location. And that promotes mercury oxidation across the SCR. And that's your primary gains of mercury control.
We have an ACI system that's never been used. So
activated carbon injection system. So that increased your mercury removal from 20 to 90%, and it reduced your mercury emissions from 2 micrograms down to 0.2 micrograms. Co-benefits: SBS removes acid gases. And so not only does it remove SO3, but it has the ability to remove HCl and HF. Where hydrochloric acid is important in terms of wet scrubbers is that dictates your blowdown rate off of your scrubbers, because you probably have some sort of chloride limit in your scrubber slurry. So if we can remove and capture HCl with SBS and capture those chlorides in the precipitator, they don't make it into the scrubber. And so it allows you to actually reduce the amount of water that needs to be treated from the scrubbers. And so that's shown here as wastewater production treated volume reduced by 70%.
And that'll be more critical when we get into ELG compliance.
And then last on the list is water consumption. This goes back to the temperature of the gas going through the precipitator. So with a wet scrubber, you have to quench that gas. And so the amount of quench water is a function of the temperature coming in. So by reducing the gas temperature 100 degrees, your your freshwater consumption was reduced significantly in terms of quenching.
Yep.